So before starting today's class, I will announce about the midterm exam. So actually, I posted the midterm logistics on the Blackboard. So you can find this midterm logistics on the Blackboard. So I also believe that this logistics are delivered to your mailbox, right? So we will take the midterm exam on this course on May 2nd. So actually, so and then the exam time, so it will start 30 minutes earlier than the regular class start time. So I think it's okay, right? So the exam time will be 1:30 p.m. to 3 p.m. So I believe it will take about 1.5 hours, but maybe faster than the, shorter than the 1.5 hours. And then, oops, oh, sorry. So, okay, I need, so, so I believe the exam place, so it should be 6:14, not 6:04. So I believe it's a 6:14. So I need to check again the mail. So actually so the classroom for the exam was assigned by the department office, and then we are assigned the Ujong Hall 6:14, not 6:04. So I think it's, so I need to check. Sorry. Oh, right. It's right. So the place is, so classroom will be, so we will take the exam at Ujong Hall 6:04. 6:04 is right. Okay. So sorry about that. So we'll take the exam at Ujong Hall 6:04. I think it's okay. It's the same, right? So I was confused. It's the same or different? It's the same room or different room? So regular classroom is 6:04, right? It's the same. No one knows. Yeah. So thank you. It's the same to our, oh, so okay, sorry about that. So I was confused when I wrote this announcement on the Blackboard. Sorry. So exam will be taken at Ujong Hall 6:04. It's the same to our regular classroom. Okay, it's the same. And then the exam will be the closed book exam. And then, so you need to remember that no electronic devices are allowed during the exam, except simple calculators. So which means that you cannot use your electric devices such as smartphone also. So, but maybe you may need simple calculators to compute some arithmetics. So please prepare those simple calculators. So if you have a COVID-19 like symptoms like high fever and then sore throat, then you can take an exam at Ujong Hall 202. So it's a different place, but you can take the exam even though you have COVID symptoms. Okay. Any questions? The 6:04 is right. I need to edit. Okay. So, okay. Any questions about the exam? Okay, so I will share my. So can you see my screen? It's a tablet screen. So, okay, good. So, in the previous class, we learned about the pipelining. So, actually, it's the pipeline architecture. So, actually, I I mentioned that in the single cycle processor, and then the clock frequency. So, it's the clock period of the our system clock of a processor is determined by critical path, the delay of the critical path. So delay of the critical path means the critical path means that is the some data path that exhibit the longest delay. So you need to remember that. So we are living real world, and then so which means that if some logic is working, then the logic generates the result after some delay, because we are living a real world. Okay, so which means that so when the data is processed by the logics, then it takes time. Then this time determines the performance of our system. So the clock frequency, which means the clock period, determines the performance of our computer system. And what is the drawback of the single cycle processor? So which means that in a single cycle processor, the delay is very long, which means that the delay of the critical path is the delay of the load instruction, which is very long. And then this delay determines the clock period or clock frequency. So which means clock period is also long, so which means that our processor will work slowly. And then in order to overcome these disadvantages of the single cycle processor, so we can apply the pipelining manner. So pipelining means that so each step can be performed within one clock period, and then if this step is completed, and then the instruction or task is delivered to the next step, and then the current step also performs the next task or next instructions. So this is the baseline mechanism. It's a mechanism. It's very simple actually. So very baseline mechanism of pipelining, right? So we actually, as you can see this in this analogy, if you apply the pipelining, then we can reduce the clock period. Okay, so which means that pipelining, the critical path is decreased because we can cut some delay of the combinational logics. So we can apply the shorter clock period. So that is the benefit of the pipelining. So also we learned about how the clock frequency of the pipeline, the architecture is decided in this example. So actually, so like our single cycle processor design, the longest delay, so which means that the longest delay of a certain pipelining stage or some step, the instruction execution step decides the clock period. So which means that, so if you see these 5 stages or 5 steps of this processor, then we can find that so the longest delay. So in this example, we can find that the longest delay is the 200 picosecond for a single stage. So this longest delay decides the clock frequency of pipeline architecture, which is the 200 picosecond, but this clock period is shorter than the clock period of a single cycle processor, which is 800 picosecond. Okay, so by applying the fast clock, then we can improve the performance of our processor. But so it's very good. So which means that we can improve the performance with the pipeline architecture. But so we need to consider hazard. So this is a very important concept. So you need to know what hazards are. So that is the meaning of the hazard. So what are hazards? What is a hazard? So you need to remember that hazards are events that cause waste of clock cycles. So which means that because of some reasons, our processor waste clock cycles, which means that some stages do nothing during these clock cycles because of some reasons. So then there are three kinds of hazard. So it's also very important. So structure hazard, data hazard, and control hazard. So we can classify these three kinds of hazard based on the causes of hazards. Okay, so the why hazard happens in our processor. So structure hazard will happen because of lack of hardware resources. So we live in a real world, so which means that, so it's also same to the real world. So the facility has the limited resource, and then many people come to use some facilities, but so we know our facility, the real facility, has the limited resources. Okay, so then many people cannot use this facility concurrently, and it's the same to our hardware component. So hardware component has the limited hardware resources, like some read and write ports, or usually data ports, okay, input and output ports. Also the number of execution engines, something like that. So structure hazard means that, so because of this lack of hardware resources, some instructions cannot be executed during a certain clock cycle. So if the required resources is busy, then clock cycles are wasted, then the performance can be degraded. And then what is data hazard? So actually, we don't need to consider structure hazard in our process architecture, also in the single cycle process architecture. So it is because we have separated instruction memory and data memory. Okay. And then how about the data hazard? So it's also very important. Actually, the data hazard are very important because because of the data hazard, the performance of our processor is degraded. So actually, the data hazard is the main source of our performance bottlenecks in a processor. Okay. So actually, we did not learn about the memory systems yet, but actually the memory is very slow compared to the processor, which means that actually, and the load instruction is executed, and then if the data is found in the main memory, such as the DRAM, then it will take a very long time to fetch this data from the data memory. So which means it is because the memory is very, very slow compared to our processor. So which means, so you can see the code like this. So actually, our data exists in our memory, and then in order to execute our code, then our code need data. Then data exists in memory. So which means that we need to use load instruction to fetch data from the memory. And then if the data is fetched from the this memory, and then so which means that the data is delivered to the register file, and then using this data in the register file, we can execute some arithmetic or other instructions, right? So what's the problem? So if the memory is very slow, so you can find the data dependency here. So actually this kind of dependency is found very frequently in our code, right? So actually our code, the main purpose of our code is to process our data, and then data exists in memory. So which means that load should be executed in our processor. And then the following instructions following instructions process these data, okay? Delivered, fetched data. So usually we can find many data dependencies in our code, but because of the data dependencies, some cycles are wasted. So, and then this is the main source of performance bottleneck in our processor, actually. Also, another hazard is the control hazard. So which means that when the branch is executed, the cycles can be wasted, right? So I will explain during in this today's class about the control hazard. So okay. So we can solve the some data hazard with the data flooding. Okay. So you need to remember that in this example, so data flooding is also very important. So actually, before data is written back to the register file, the result of a certain instruction can be generated. So for example, if we execute the add instruction, actually the result of the add instruction is generated just during execution stage, so just after ALU. And then, and then if the following instruction is also the arithmetic instruction, and then actually this arithmetic instruction requires operands before the ALU processes these operands, okay? So in the pipelining, that we can check the future and past. So it's the timing of our data generation and then data consumption. So data production and then data consumption, okay? So in this diagram, so actually, so in this example, so we can know that when the add instruction is executed, the result of this add instruction is written back during this stage, so write back stage. But when the add instruction is executed, then the result is generated at this point. And then also when the sub instruction is executed, sub instruction requires its operands during EX stage of the sub instruction. Actually, at this point, and then if we check the timing of the data production, and then data consumption, then we can know that the data is produced before when data is required. Okay, so and then the processor already has this result, okay, in a pipeline. So we can deliver this result to the input of the ALU. Okay, so this is the data folding. So with the data folding, we can solve the data hazard by data dependencies between arithmetic or logic instructions. Okay, so which means that the instructions that use ALU. But for some instructions, such as the load instruction, so when the load instruction is executed, then this load instruction needs to access data memory. Okay, that's during the memory stage. So which means that the result of this load instruction is generated during the memory stage. So that is the actually late part of memory stage. Okay, because this data memory has also delay. So the result is generated at this point, right? And then, so actually when the sub instruction is executed, usually, so which means the instruction fetch is here, instruction decoding is here, and execution is here. So when the sub instruction is executed at this point, then this is the ALU, and then which means that this sub instruction requires its operand at this point. So we can check the timing of data production and then data consumption in this case also. Okay. So so this is the future and this is the past. So actually, we cannot. so we cannot get a result of the. We cannot get the future result, right? It's obvious. Okay. So we cannot get future result currently. So it's not possible. The sub instruction cannot be executed at this timing. So we need to make sub instruction wait 1 clock. So which means that the execution stage of the sub instruction is during this time frame. That's like, so this time period. So the result of this memory can be forwarded to the input of the ALU. So which means that 1 clock is delayed for this sub instruction, right? So this is called the load use data hazard. So which means that when the former instruction is arithmetic or logical instructions, then we can solve a data hazard using data forwarding, right? But if the former instruction is load instruction, which means that the result of the load instruction is produced during memory stage. So then if the very next instruction requires the data from this former load instruction, then the next instruction needs to wait for 1 clock cycle. Okay, so 1 clock is wasted. So it is equivalent that, so for this case, the sub instruction consumes 2 cycles because of data hazard. So if there is no data hazard, then the clock cycles are not wasted. So which means that for the pipeline architecture, the CPI is 1 if no hazard. No hazard. But because of hazard, the CPI of a pipeline processor is bigger than 1 because the cycles are wasted. So for example, in this example, the sub instruction consumes 2 cycles because the sub instruction wait 1 cycles. Okay. So because of a data hazard, the performance of a pipeline processor can be degraded. And then we want a good processor, which means that the processor works very fast. So which means that processor exhibit the high performance. But because of the hazard, the CPI is bigger than 1. So which means that the performance is degraded by hazard. And how can we solve this issue? So we can solve this issue using compiler optimization. So what does that mean? So if you see this code, then you can find that, oh, this code performs this C code, A equal B plus E, and then C equal B plus F. So, and then, you know, after two load instructions are executed. So we need to fetch some required data from the memory, and then the add instruction consume the result of this load instruction. And what's the problem? Because of load use hazard, then we need to waste 1 clock for this add instruction. So add instruction need to wait for 1 clock. So actually it takes 2 cycles for executing this add instruction, right? So you can find another load use hazard here. So so if you see this example, so 2 cycles are wasted for executing this add instruction and then this add instruction. But we can avoid this case with some code scheduling, so code rescheduling, which means that the compilers can change the order of instructions by considering load use hazard. Okay, so what does that mean? If there are some independent instructions between load and add, then we can execute these independent instructions. And then after some cycles, this add instruction can be executed. But when this add instruction is executed, a processor, the pipeline processor already have the result of load instruction. Why? The cycles are taken by independent instructions. Okay, so for example, so we can find the data dependency between this load and add. And then by changing the position of this load instruction, so you know this load instruction is independent from this load and this add instructions, right? So compiler changed the location of this load instruction. So which means that between this load and add instruction, independent instruction can be executed. So this instruction takes 1 cycle. And also between this load and add instruction, there are 2 independent instructions. So this X4 can receive data from load instruction without any data hazard. Right. So we can reduce the cycle for this code, the optimized code. You understand? So which means that by adjusting the order of instructions, we can also solve some data hazard issues. Okay, but in order to optimize, apply this compiler optimization like the code scheduling, then the compiler needs to know the detailed architecture of a processor. Okay, but it's very difficult actually. Okay, let's think about the control hazard. So why the clock cycles can be wasted due to a branch instruction? So it's conditional branch instructions. So think like this. So let us assume that it's PQ, X1, X2, and target. And I believe everyone knows the behavior of this branch instruction. So the branch instruction, check the X1 equal X2. And then if the condition is true, then PC is the PC plus target multiplied by 2, it's a risk 5. And then if false, PC is PC plus 4. So this is the normal instruction fetch. So what does that mean? So this is the BQ, and then you can find some next instruction here, and then you can find the target here, target instruction here, and then some no other next instructions. So if the branch is false, then next instructions can be executed like other normal instructions. So what does that mean? In a processor like add, sub, and load, so these are normal instructions. Which means that these instructions are not control instructions. So which means that the instructions are executed sequentially. So which means the PC becomes the PC plus 4. The PC plus 4 is the program count of the counter of the next instruction. So PC is incremented by 4, and then next instruction is fetched and executed, and then PC is incremented by 4, and then also the next instruction is fetched and executed sequentially. But when the branch instruction is executed, and then, but if the condition of the branch is false, then it's the same to the normal instruction. So which means that the next instruction is fetched and executed. So in this case, the clock cycles are not wasted, right? It's the same to the normal instructions. But the problem is that when the branch condition is true, then we need to jump to the target of the branch. But if we see that this branch instruction, then we need to check so we need to compare the data from 2 source registers, right? Then in order to compare the 2 data, then we need to apply sub, right? Subtraction. And then you need to use the sub, and then in the single cycle process design, the comparison is performed by ALU, right? Performed by ALU. So which means that during the EX stage, this comparison is performed. So what does that mean? We can know the result of a branch instruction actually during the EX stage. Now what's the problem? So in a single cycle processor architecture, even though the branch is taken, so which means that condition of the branch is true, the clock cycles are not wasted, right? Because the branch is reserved within 1 clock period. But in the pipeline architecture, like okay, so branch is here, and then branch is in the instruction fetch stage, ID stage, and EX stage. What does that mean? There can be the next instructions here. So when the branch is in the EX stage, the next instruction I1 is in the ID stage, right? Also, the next instruction I2 is in the IF stage. So these instructions are instructions when the branch is false. So branch is not taken. But if the branch is true, then these instructions, we cannot execute these instructions. So when the branch is taken, we need to cancel these instructions in the pipeline. So cycles are wasted. So this is the control hazard. So control hazard means that because of the control instructions like branch instructions or jump instructions, then clock cycles can be wasted. So then these events are called control hazards. Okay. So in a pipeline architecture, we cannot avoid control hazard. So then, but we need to avoid we need to reduce some number of wasted cycles by control hazard. So we can apply some techniques, architectural techniques like the branch prediction or some techniques here. So I will explain about the branch prediction and then add some techniques in the later part of this chapter, not today. So you need to, so you can just remember that because of the branch instruction, actually the taken branch, so it means that the condition of the branch instruction is true, then clock cycles are wasted. Okay, so because of this waste of clock cycles, performance is degraded. So that is the control hazard. Okay, so I will explain about the branch prediction later. So pipeline summary. So I will summarize the pipelining. So we can improve the performance of our processor with pipelining. Okay, obviously. And then I already explained that when a pipelining is applied to our processor, then latency is improved or throughput is improved. Okay, you can find that it's throughput. So throughput is improved. How can we improve throughput of a processor? It is because if you see some time period of the pipelining, right? And then during some same time period, we can find that many instructions. What do you mean? So many instructions like add, write the backstage, and then load of the memory stage, and then some solve of the EX stage, and branch ID stage, and then solve another solve the instruction fetch stage. So if you see a certain time period, some time, then we can find that many instructions, the multiple instructions are being executed by pipeline processor. So like this example. So our pipeline architecture is composed of 5 stages. So which means that we can find usually, just ignore the hazard. So usually if there is no hazard, then we can find 5 instructions which are running in our processor, right? Like this example. So we can find an instruction which is in the write back stage. So we can find another instruction in memory stage execution ID instruction fetch. What does that mean? With the pipelining, multiple instructions can be executed concurrently. Understand? Multiple instructions can be executed concurrently at the same time. So by executing multiple instructions, we can improve the throughput. Also, we can improve the performance of our processor. So this is called the parallelism. So it's not easy to translate this word parallelism. It can be translated like 병렬화 in Korean, but you can just understand that parallelism means that multiple tasks or multiple things can be executed concurrently. So with the pipelining architecture, we can think that multiple instructions can be executed in parallel. So parallelism. So this parallelism is called instruction. Okay, I will just here. We can call this parallelism as instruction level parallelism. Okay, so this parallelism is called instruction level parallelism, which means that multiple instructions are executed concurrently. And then in a abbreviation form, it is called ILP, instruction level parallelism. So, which means that because many instructions are executed in parallel, it's called the instruction level. So we can imagine other level of parallelism in the computer, such as the thread level parallelism, like TLP. And so for example, so we can think like think about some multi-core architecture. So with the multi-core architecture, multiple threads. Thread is very similar to the process in Windows. So we can observe that many processes or many threads are running on our computer processor. So it can be called the thread level parallelism. So there can be the different kind of parallelism in our computer systems. But so we are learning about the pipelining of process architecture, and then pipelining exploit instruction level parallelism. So which means that multiple instructions are executed concurrently. And then also this is very important. So there are three kinds of hazards, and then there are structure, data, and control hazard. Okay. So the baseline concept of pipelining is very simple, right? It's very simple, but we need to consider the hazard, and then in order to reduce some performance degradation by this hazard, then we need to add some techniques, hardware techniques or software techniques like a compiler optimization. So that's why when pipelining is applied, the process architecture becomes more complex. That's why it's getting more difficult. Okay. So, yeah. Oh, it's a good question. So actually, so someone is, I believe everyone can read the, see the question. Right back, instruction fetch. So which means that, so it defines the actually read. So it represents the read of in the memory or register file. So which means that in the instruction decoding, the instruction needs to read operands from or register file. So which means that so it just use this port. So actually read out port from the register file. So that is colored. So actually the half part, the later half part is colored in this register file, and then the write back stage. So actually, the data is given to the right port of the register file. So that's why the half of the register file is colored. Okay. So the midterm will cover until this slide, as I announced it. Team. 두 개가 맞는데요? Why do you think it's three cycles? Because actually we avoid the data a pipeline stores by data hazard for this point and this point. So actually we waste 2 cycles by data hazard, and then by adjusting the order of the instruction, then we can avoid the data hazard for this case. So we can reduce the wasted clocks, like 2 cycles. 왜 3개가 되죠? 네, 여기서 하나 줄이고 요거 하나 줄여서 2개 줄이는 것 같아요. So data hazard for this. Okay, got it. Okay, our midterm will cover until this page. Okay, then let's dive into the detailed architecture. Let's dive into some detailed design of the pipeline processor. Okay, so actually in the early part of the chapter 4, we learned how to design single cycle processor. So we are learning about the pipeline architecture, so which means that we need to learn how to design pipeline processor. Then, so when we design a single cycle processor, we start from the data path element, and then we connect the data path, which means that the input and output ports of the data path element. And then we define the control port of the this data path element. Then we added the control unit. And then what is the basic concept of pipelining? Basic concept of pipelining. The basic concept of pipelining is to just split the required steps for executing instructions. So which means that actually in a single cycle processor design, we define 5 steps for executing instructions. So, and then in a pipeline design, pipeline architecture, then we split these steps to the individual stages. Okay. So what does that mean? This slide shows the this slide shows the single cycle processor design, right? Do you agree? So, and then we can divide some data path components and then divide some steps in the single cycle processor like this. So we can, so this is the instruction fetch, instruction decoding, execution, memory, and write back. Also, each step requires some specific data path element. So for example, in the instruction fetch stage, we require the PC update and instruction memory, right? And then for the ID stage, then the instruction is decoded, and then we need operands from register file, right? So which means that we need the register file. The execution stage, we need the ALU, the data memory, and then we need also register, but it's write part. This is the read part. So the first step for designing pipeline architecture is to just split the single cycle processor. So this is the instruction fetch part, like here, and then this is the instruction decoding, execution, and memory, and then here. Also, in this slide, so this part, so we just assume that, oh, these are the delays of each step of the single cycle processor. So actually, these delays are caused by data path element of each step, okay, or each stage. So it's very so So in the instruction fetch stage, then you can find, oh, instruction memory is the some representative data path element. And then, the instruction memory may take some delays. So it just split instruction here. And then the idle stage is also the same with the same mechanism, with the same concept. Then the register file will take some delays. So we just split the some steps between idle stage and EX stage. So we can split each step of the single cycle processor. So what does that mean? In a single cycle processor, these are combinational logic. And then these data path elements are executed sequentially. And then during one clock cycle, this clock cycle, then executions of these data path elements are completed. So during this time period, okay, understand? And then when we apply the pipelining, this is the one stage. So which means this is the clock cycle. So during this clock period, instruction fetch complete each operation, and it's the same to other stages. During this clock period, it's the same clock period actually, we need to use the same clock signal. Because during this clock period, instruction decoding needs to complete its operation. Then how can we implement this? So when you learned about the basic conventions of digital design, I explained that digital design looks like this. This is the D flip-flop, and then this D flip-flop is sampled by clock signal, and then there are combinational logic, and then also you can find another D flip-flop. This is the clock. So what is the purpose of these D flip-flops? So D flip-flop just sample the input of the input signal with at the rising edge of the clock. Okay, so which means that at this timing, this D flip-flop provides input signals for combinational logic. So which means that these inputs are given to this combinational logic at this timing. Okay, and then it will take time. So we can find some delay in this combinational logic. After some time, the result of this combination logic will be generated, like at this time. And then in the pipeline architecture, this result should be delivered to the next stage, right? So it's actually this, after this D flip-flop, there is the next stage. So then in order to provide the inputs, so inputs of next stage at the same time, at the same timing, then the output of this combinational logic is sampled by this rising edge of the clock at this point by this D flip-flop. Do you understand? So that is the basic convention of the digital design. Now, how can we design the pipelining? So in this pipelining, so let's think about this. So you can find that, this is the input of the instruction memory, right? And then the result is of the instruction memory is generated at this time, actually at the output port of this instruction memory. But there is some delay here. So what does that mean? This is the input of this combinational logic. And then based on the design conventions, this input is given to instruction memory at the rising edge of the clock. Okay. And then this is the output. This output should be delivered to the next stage. So what is the next stage? This next stage is the instruction decoding. So this output of the instruction memory should be sampled by D flip-flops, and then at the rising edge of the clock, and then this result is delivered to the next stage, ID stage, by D flip-flop. Do you understand? It's the same to the instruction decoding stage. For this register file, this D flip-flop provides the input signals. Then after some time, the output is generated. This output is also sampled by D flip-flop. So how can we implement the pipelining? Oops. We can implement the pipelining with the actually D flip-flops. So these D flip-flops are called the pipeline register. And then this pipeline register is sampled by the same clock. So do you understand? So even though these pipeline registers are called registers, so it is different. So those registers are different from general purpose registers in RISC-V. Okay, so we need to distinguish these pipeline registers with some general purpose registers. So actually, these registers are D flip-flop of our digital design. So and then we use these D flip-flops for sampling output of the previous stage, and then D flip-flop provide input signals to the next stage. Understand? So how can you split each stage of the pipelining? We can just insert the D flip-flops, and then these D flip-flops are sampled by the same clock signal. Okay, so the output of this former stage is delivered at the rising edge of the clock. So this is the first start of the pipelining design. So we split each stages of the single cycle processor architecture, and then between two stages, between two neighbor stages, then we just insert the D flip-flops working with the clock signal. So by adding D flip-flops here and here and here and here, then we can reduce the clock period within just longer than the delay of the longest some data path. Okay, so if we just insert the D flip-flops like this, like the pipeline registers, then we can apply the fast clock signal. Okay, so and then we use the instruction fetch and the ID stage reg to represent the pipeline registers between instruction fetch and instruction decoding stage. And then also we can use the ID EX for representing these pipeline registers. 네, 맞습니다. 네, 포지티브 엣지에서 데이터가 샘플이 리졸트가 샘플이 된 다음에 그 다음에 다음 클락으로 이제 넘어가니까는 네, 그렇게 이제 이해를 하면 됩니다. And then this pipeline register is called ex/mem. Then this pipeline stage is called mem/writeback. So I will use this naming convention for represent the pipelining registers. Okay. Then let's see how pipelines work in the process of design. So actually in a single cycle process of design, it was very simple. So actually every instruction completes its operation within one clock. But in the pipeline architecture, the instructions need to go through multiple stages of pipelines. And then, which means that at some time, some clock period, the instruction is in the instruction fetch stage, and after some clock period, then instruction is in the ID stage, and then after some period, then the instruction is in the EX stage. And then, so we need to represent this some behavior of instruction executions in the pipeline architecture. So it's a little bit more complex than the single cycle processor execution. Okay. Then let's see how the instructions are executed in the pipeline processor. Okay. And then this slide explain how the load instruction is executed in a pipeline processor. So it's called the CC1. It's a clock count 1. So during this clock count 1, the instruction is fetched. So actually, when I already explained that the clock is also connected to this program counter register. So which means that program counter just generate the new program counter value at the rising edge of the clock. Okay, so this is the start point. So this is the PC value. So which means that this is the current PC value. So current PC. So PC is given to the address port of the instruction memory. Then the instruction is generated. So it looks like this. So at the rising edge of the clock, the program counter generates the PC here. So this PC is given to the combinational logic, like instruction memory, right? And after some delay, and this delay is shorter than the clock period, instruction is out from the instruction memory. Okay. And then this instruction is sampled by instruction fetch and instruction decoding pipeline register at the rising edge of the clock. So it's sampled by this point. Do you understand? So after that, in the next clock cycle, the CC2 is a clock count number 2. This pipeline register provide the sampled instruction to the ID stage. Understand? So CC equal 2 is a clock count number 2. It does the CC equal 1. So instruction. So this is the instruction from instruction memory. This instruction is given to the another data path element register file. Okay. during the ID stage. It's ID stage. So this is the register file, and then also it will take time to read the data from the register file. So these data, read data 1, read data 2, also the immediate generator generate the immediate data from the instruction. So this output of ID stage is sampled by clock signal at the ID EX pipeline register. So understand? So the output of these signals are sampled by pipeline register. So after this rising edge, the output of these ID stages are delivered to the EX stage. Okay. So the EX stage, for the load instruction, we need to use the ALU to generate the address of the load instruction. So during this clock period, the ALU is used, and then ALU generate the output. So these outputs are also sampled by EX memory pipeline register, and then it's a load instruction. So the data memory is accessed. So what is the input of the data memory? The processed, the result output of the ALU. So during this, it's a CC, the clock count number 4. So at the clock count number 4, the output of ALU is given to the data memory, and then data is read from data memory. Okay. And then the clock cycle number 4, this data is written back to the register file. Oh, no, 5. Sorry, it's clock count number 5. The clock count number 5. It's a CC5. Then the result of this load instruction is written back to the register file. Then what's the problem? So you can find that this text box is a wrong register number. Why? So if I can. If you see the input of this register file, so the load instruction is in the write back stage here. Then which instruction is in the ID stage? So if you see the timing of this instruction is different instruction. This is not a load instruction. Do you understand? So, at clock cycle number 5, the load instruction is in the write back stage. Understand? But in the ID stage, some other instructions, it's not load instruction, like some add instruction maybe. Some other instructions are in the instruction stage. So what's the problem? The write data is the data by load. Understand? But this write to register number, so like RD of the instruction is so you can say that, you can find that, this is connected to the write to register. If this instruction is connected to write to register, then this RD is not the RD of load. This is the RD of add instruction. Are you following me? What's the problem? The data is, so when the data is written back to the register 5, the data is the data of the load instruction, but the destination register is not the RD of the load instruction. How can we solve this issue? How can we solve this issue? So in the previous slide, so we assumed that when the CC is 1, the write back load instruction is here in the instruction fetch stage, and then CC2, the load is here. Then so which means that at the CC equal 5, the load is here. Then how can we match the timing of this RD of the load instruction? So which means that we can also make the RD of the load instruction to pass through the pipeline registers. Okay, so like this. So in this example, this is the RD. If you see this path, then RD is propagated via pipeline registers. So which means that when the CC5, when the load is here, then the RD of load is here, right? And then this RD of load is connected to the write register port of the register file. Do you understand? So so in the pipelining architecture, we need to align the timing of data and then timing of some other signals like the destination register number. Also, we need to align the timing of control signals. That's why the pipelining design is a little bit, it's more difficult than the single cycle processor design. So important thing of the pipelining design is that we need to align some appropriate timing of data and control signals like the RD of the load instruction and then data of the load instruction. Okay, so it's like a piggyback. So it's a piggyback of signals and control signals or some other signals. So which means that when the basic concept of this timing alignment is that so you can think like this. During the write back stage, then we need to store data to register file with the RD and some data. So which means that RD and data should be the RD and data should be the data of the same timing. Do you understand? So which means that when the data is written back to the register file, then we need to use the same timing of the RD. Okay, that is some basic concept of the pipelining design. And then it is called the piggyback. 피기백이 뭐냐면 어부바 하는 거거든요. 그러니까 어부바 하면은 같이 이렇게 움직이는 거잖아요. 어부바에서 같이 움직이는. 그래서 이 파이프라이닝에서 so in the pipelining data and then control signals to work together. So it's called the piggyback. Okay, so it's the same to the. So we can also think about the store instructions here, and then it's the same to the actually control signals. So control signals also we need to also align the control signals for appropriate time in the pipeline architecture. So which means that, so for example, if the control signals is required during in the memory stage, so which means that the control signals also pass through the pipeline registers. So which means that we need to align the timing of these control signals and the instruction. the data of the instruction. Okay, so that is the main main convention of the pipelining design. Okay, and it's very important. So some students think that pipelining is a little bit difficult, it's a little bit tricky because of the timing. So we need to align the timing of the data and then some control signals in the pipeline design. But just remember that you need to, when the data is processed, then we also align the timing of this data and then some required signals in the pipeline design. Okay, it's very, very important. Okay, so I will stop here, and then do you have any questions? Okay, okay, thank you for your attention, and then okay, thank you for your attention, and then you can ask questions after class. Then see you in the next Monday, and then see you in the next Monday in person during the exam. Okay. See you guys, and then good luck for the exam.